Hey everyone, today we're going to take a look at free fall and freely falling objects and why exactly objects free fall uh, on Earth. They'll fall towards Earth, and that really has to do with a force that's actually pulling objects towards the surface of Earth. And things wouldn't free fall or fall freely if we didn't involve gravity. So in order to really understand what free fall is, we need to know what gravity is, because that's what's going to cause free fall. So gravity, which is represented with the lowercase g, is actually a force. And it's the force that acts between the mass of Earth, really the mass of any object, but Earth is so big that this really has a large effect, especially with things on or near the Earth. So it's the force between the mass of Earth and the mass of any object that is in the vicinity of Earth. The closer that we are to Earth, the stronger the force of gravity is going to be. The farther we move away from it, the lower the force is going to be. But it never actually disappears. It just kind of gets infinitely small. So G is represented with the units of meters per second squared, which means G is also considered an acceleration. And it's going to be considered the acceleration in the vertical direction. So we talk about free fall, freely falling objects. G, our symbol for gravity, can also be replaced with our symbol for acceleration. So G is kind of equal to our acceleration. Now on Earth, G is equal to 9.81 meters per second squared. And we can find this on the front of our reference table. This is on page 1, which lists our physical constants. If you're looking for that, that's where we can find that. Page 1 of the reference table, under the physical constants section. So we can find that there. Now, as far as gravity and acceleration and how they relate to free fall, we're going to want to kind of define what free fall means. Now, when we talk about free fall problems, when you come across any free fall problems, the force of gravity is the only force acting on the object. We disregard other forces that might be accelerating or slowing the object down. We assume that the only thing that's going to be changing the motion of the object is going to be the force of gravity. Now, if we go to the back of your reference table, there's a few different equations that we'll be using. But really what we're going to be focused on, I'll change the color of this here, is the equation D equals VIT plus 1/2 AT squared. I do my T's with a little bit of a loop on there as to kind of discern them away from the plus sign. Let's see. That's going to take a couple different forms depending on what our initial velocity of the object might be. So oftentimes this equation will look slightly different as d equals 1/2 at squared when the initial velocity of the object is 0. We kind of just, because vi times t, if our initial velocity is 0, that whole product there would also be 0. So those are the two that we're going to kind of see. You also might see our equation to calculate acceleration, v equals at. We also might see it as v equals gt. When you see it with the g in there, we're assuming that our acceleration value is going to be acceleration due to gravity. So they can kind of be used synonymously depending on the scenario. So when we're dealing with free-falling objects, if the object happens to be moving upward, and we'll look at both these cases here in a second, due to the acceleration moving downwards on the Earth, which is always the force moving in the direction towards Earth, not away from Earth, the object's moving upward, the object's velocity is going to decrease. So moving in the opposite direction of our acceleration, the object's velocity is going to decrease. Again, in free fall, if the object's moving downwards or in the same direction as our acceleration or the force due to gravity, that's going to cause our velocity to increase. So when they're both moving in the same direction, our velocity will increase. When they're moving in opposite directions, our velocity will decrease. Remember that acceleration, or g, is always pointing downwards towards Earth. And we usually call that a negative value. The magnitude would be 9.81. We generally see it as a negative value unless we're referring to some other scenario, which we don't really see. I'll leave that off there for now. So let's look at an example here of an object free falling from a ledge. And this usually tells you somewhere in the problem that it is a free fall problem. So I'm going to set up our table here. Make sure you're doing the same. Acceleration. Hopefully you start to see that this is a rather valuable tool to use. So a rock's dropped from a bridge 100 meters above water over a river. Locate the rock after 3 seconds of free fall. So we have some kind of bridge here. There's my bridge. We have a rock that's going to fall down to the river below. Again, I encourage you to sketch here. We know this distance is 100 meters. After 3 seconds, we want to see where we can locate the rock. So draw sketches to try and see where things might be moving to get a better understanding of what the question is asking. Make sure you are defining everything that you have. So we know that the time of free fall is 3 seconds. We know acceleration due to gravity, 9.81 meters per second squared. We know that our initial velocity is 0 meters per second since we're dropping it from the ledge. We don't know final velocity, we don't know average, we don't know the distance. So let's see what we can do here. Using our blue equation here, d equals 1/2 at squared, we could use either or. I guess we'll start with the original so you can kind of see what this does. We'll start with our distance equation, including our initial velocity, plus 1/2 at squared. If we plug in here, initial velocity is 0 meters per second. So regardless of what our time is, that whole product there is going to be 0. This is 9.81 meters per second squared. And our time is 3 seconds squared. This is D, so D equals, this value is 0, so it's 0 plus, let's see, we're going to have 9.81 over 2 times 9. Punching this into our calculator, we get a distance of 44.145, which would round to 40 meters. Now that just kind of tells us that it's fallen 40 meters. If we want to locate the rock, we kind of need a little bit more there. So what I'm going to say is, well, we dropped it from 100 meters. If it fell 40 meters, where is it? Well, it is 60 meters above the ground. We could also say it's 40 meters below the surface from which you dropped. I kind of like the answer here of saying that it's above the ground. To me, it seems to make more sense as far as locating where it is. If we wanted to here, which, yes, I want to, determine our final velocity, we're going to use a different equation. I'll do this in green here. To find the final velocity, we can take our initial velocity plus our acceleration times time. Initial velocity is 0 plus 9.81 for 3 seconds. Now acceleration tells us that our velocity is going to change by 9.81 meters per second every second. So if we multiply that times 3, we can actually get our final velocity. This comes out to 29.43 meters per second, which is equal to 30 meters per second. And to find the average velocity where an object is accelerating uniformly, such as in free fall, we can use our midpoint average velocity formula. We know the final was, let's call it 30 meters per second plus 0 meters per second over 2, which will get us 15 meters per second. This question is not exactly set up very well to determine that. That would round up to 20 meters per second, which this will use 20 meters per second. You can see the error in there. This question would have been a lot nicer if it was 100 point. It is not. So that's going to make our numbers rounded off with a lot more error. And we know that our distance that it fell, we'll put in here that it was 40 meters. Now this next one is a little bit more challenging. I'll do this in a different color. Ball is thrown straight up in the air at a velocity of 39 meters per second. Find the distance the ball traveled in 6 seconds. So we have this ball, and the ball is going to travel upwards with a velocity of 39 meters per second. Now we know the initial velocity is equal to 39 meters per second. We know acceleration is equal to 9.81 meters per second squared. And our time that this ball is going to travel is 6 seconds. Now acceleration, if we throw the ball upwards, acceleration is going to act in the downwards direction. So in this case, our acceleration is going to be negative if we call the direction of the ball moving upwards the positive direction. So there's a couple ways that we're going to take a look at this. We need to figure out, well, is the ball going up for 6 seconds, or is it going up for part of that and then coming down for part of that? So in order to figure that out, we can use our acceleration equation, A equals delta V over T, which if we reorganize this here, becomes, if we solve it for time, delta V over A. Which if we look at this here, change in velocity, which would be 39 meters per second. Again, that's a change, so that's final minus initial, 0 minus 39, over the acceleration of, we'll take the absolute value of that, 9.81 meters per second squared. This comes out to 3.97 seconds, which is also equal to, let's call it 4.0 seconds. So in order, we're going to have two different things here. See if I can organize this appropriately. Of that 6 seconds, it's going to take 4 seconds for that ball to reach the top of its trajectory before it starts falling back down. So this ball is going to go up, and then it's going to start falling back down. So as it goes up, time it's going to take is about 4 seconds of that 6 seconds. I'll do the other one over here. It's then going to fall down. If the total time the ball is traveling is 6 seconds, time falling down is going to be 2 seconds. Because again, we have a total flight time of 6 seconds. So I'm going to calculate the distance the ball travels in its upward trajectory, and then look at the distance it travels on its way down. So on its way up, we're going to use D equals VIT plus 1/2 AT squared. Now we do have an initial velocity here. It's 39 meters per second, and that occurs for 4 seconds. We add in the other half here, that's going to decrease our velocity. And our time again would be 4.0 seconds squared. Punching this into the calculator, and again do this extremely carefully as this seems to be the source of a lot of error. The ball travels 77.2 meters in the upwards direction, in the positive direction. Well, it's not fully our answer yet, because that's how far it traveled in the first 4 seconds. We're now going to have to figure out how far it takes to travel its last 2 seconds. When the ball reaches its top, the velocity here is equal to 0. The ball is traveling upwards. It has to stop completely before it starts moving back downwards. So we're going to use the same equation here. D equals VIT plus 1/2 AT squared. Our initial velocity here is 0. So for the 2 seconds there, it doesn't quite matter. We have 9.81 meters per second squared for our acceleration times that time of 2.0 seconds squared. Punching this in, we get a distance equal to 19.62 meters, which would round to, looks like we have 20 meters. This would round to 77 meters. And again, this would be in the down direction. If we add these two together, we can get total distance traveled by the ball. So we'll have to kind of be conscious of that with a couple of these examples where the motion of the ball might not be in one direction, it might be changing direction. So we're going to have to be conscious of that. If you guys have questions on this, make sure you raise them in class. On Monday, we'll do a little bit of practice with this. For today, I'll leave you with a joke. Student riding in a train looks up and sees Einstein sitting next to him. Excited, he asks, "Excuse me, Professor, does Boston stop at this train?" Have a great weekend. See you guys on Monday.